Okay, so for the talk one, this session is all about making smart choices about the data store that you are going to use for your system. Now, as your system advances, your data requirements grow, and then you have to scale your system for that particular data requirements. And this talk is going to walk you right through that requirement, that how you're going to dynamically scale your system while you are actually working on that system, and then make it scalable for full grade data scores. So I would like to welcome Vinayak and Vignesh on the stage. A little bit of introduction about Vinayak and Vignesh. Vinayak comes with 9 years of experience, and he specializes in building and optimizing large-scale data systems. He has diverse experience of working with industries like finance, automobile, and insurances. He has worked on technologies like Java, Kafka, and Kubernetes. And he always liked to solve complex challenges. So if you want to build a scalable, high-performance system that's robust, then I think Vinayak is the key player who will help you. And we have Vignesh as well with us. So Vignesh has experience of working with Java, Kafka, and NoSQL databases. He has built interactive systems in Python, systems which are high-performance system in automotive industry as well. And if you want to solve, again, any complex problem, Vignesh's ability of thinking from first principles will always help you in those problems. So I'll pass on mic to these two guys and grab the stage.
All the best.
You can carry. Thank you, Shruti, for the wonderful introduction. I hope I'm audible at the back. Okay, cool. So we are going to talk about a specific challenge that we faced as a war story while building a solution. So the Act 1 is basically a calm before the storm. Basically, everything is calm and everything is going right as you are expecting, and suddenly one day it doesn't go right. So that's the Act 1. We'll talk about what that stage is basically. So as I mentioned, we were building this vehicle telematics platform for one of our clients, and basically that platform was serving both the individual vehicles as well as the cargo vehicles and the trucks. So these vehicles were basically sending information over to the platform, and that information was basically needed by the end users. End users are basically your vehicle owners, people like you and me who own vehicles, and they want to track and see where the vehicle is. And then there are users like fleet owner who wants to see where are the vehicles and what is the efficiency of those vehicles. So at this particular time, we are close to serving like 1 million vehicles, and we get like close to 2 terabytes of data per day. So this is just to highlight the volume of the data that we handle onto the platform. So yeah, as I mentioned, the users wanted live tracking. They needed to know where the vehicle is it healthy, then is it functioning correctly, then when you are going outside, if you want to share your location with your family, then the live location sharing was also done by the end users. So these are some of the features that the end users used onto the platform. Second one was troubleshooting. Basically, let's say your car is running out of coolant, and suddenly your engine will start overheating and you will have other issues into the car, right? So what if we can tell you that, okay, the coolant is about to run out, go and replace it. So that's kind of preventive maintenance that we wanted to do. And similarly, the example of faulty batteries, right? Whether before the urea in the battery runs out, you should get a notification that, okay, it is about to run out, and you should go and change it. So those kind of troubleshooting information or insights the users wanted that reduce their overall maintenance cost in the long run. And the final case was like available vehicles. As we mentioned, like there are cargo vehicles. So if there is a cargo vehicle that is available nearby, so we wanted to tell that to the users also. These are some of the use cases that we'll be looking at. The overall vehicle telematics platform supports a bunch of use cases. These are one slice of it. Okay, so let's talk about the flow, how the data basically lands into the platform. So as I mentioned, there are vehicles. Vehicles have devices installed. Those devices basically generate data in an interval manner. That data is basically sent over a cellular network. So that and it basically travels in a protobuf format. Protobuf is basically a binary format where the data is sent as a compacted data rather than sending it as a full-fledged information, which saves the bandwidth onto the cellular networks. And then that data basically is received by a MQTT broker. MQTT is basically your telematics transport for the IoT devices. So that broker basically receives the data, and then the process transforms the data into understandable like a JSON format, which is easier for systems to debug and understand and see the flow of the data, where it is going. And then finally that data basically lands onto the Kafka streams that we maintain. So overall flow of the data from the vehicle to the Kafka almost happens like in milliseconds or seconds, you can assume. Yeah, so we'll now just talk about what are the types of messages that the vehicle sent. The first type of message is like a health message. I mean, everybody can understand a JSON format. So it indicates basically a vehicle, what vehicle sent that message, at what time the vehicle message was sent, and then the health parameters of that vehicle. As you can see in the example, it indicates a tire pressure. What is the tire pressure in that tire at this moment, basically. So you can imagine vehicle has like lot of moving parts. So it will have like lot of parameters that are sent. So I mean, at this moment, it got a tire pressure reading. So it has sent the tire pressure reading. You can imagine not all of the signals will be sent at the same time, but they will be sent when they are available into the system. So I mean, so this is one type of message. The second is basically the telemetry message. The telemetry more on talks about where the vehicle is, what is the fuel level, what is my, let's say if it is an EV vehicle, what is the battery, all of that. So that's your basic telemetry that you get with any sort of, IoT device. And final one is basically an event. This will indicate, let's say vehicle is taking a very rapid speeding. So that can also become an event that vehicle has done this. So the events basically indicate where it had happened and what was the, let's say if you're over speeding, what was the speed at that time. So those are the events that basically get generated. And these events are generated as they are happening. You can imagine these are sent on, the health and telemetry is sent on an interval, but event is sent as it is happening. Okay, going to the constraints part of the problem. So at that time, we had almost 400K vehicles and each vehicle sent the health message every 30 seconds and even along with the telemetry, and the event messages were generated as they are happening. One important note for the health message is because the parameters are so many, let's say at one time you are getting 10 parameters, but overall over a period of time, the same vehicle might have sent like let's say 1000 odd parameters. So those 1000 odd parameters still the users wanted to see them. Like even if it's a stale value or a last known value, we had to show that value to the user. So that was a scale constraint. Then so the user should be able to see the latest data of a particular vehicle, and it should happen like within 30 seconds because the frequency we were maintaining like was 30 seconds. So it should get updated within those 30 seconds. Yeah, and the message size, because the health message has variable parameters, the size was going over 1 megabyte as well at times. And that means every 30 seconds we were like writing or generating almost hundreds of GBs of uncompressed data that we were ingesting into the system. So these were the problem statement or the use case that we were solving. And the first solution that we did was using a simple solution like a Postgres. So we already had you remember we talked about getting the data onto the Kafka. So the data is available in the Kafka and it is partitioned by the vehicle ID. That means for a single vehicle, that data will be processed by one particular consumer. So there is no concurrency, but still there is no concurrency. Only one consumer is updating the data at a time. So you can imagine the consumer is basically consuming the data from the Kafka and then persisting that data into the Postgres application. And the users were consuming that through the APIs in one single shot. I mean, the consumer and application is like a same or a single application. For the flow perspective, we have shown it as a two different things, but it is a single application, you can imagine. And this was a schema structure that we used. Like basically your primary key is your vehicle ID and the event date time at which we received it and the compressed, the JSON-B data that we just saw earlier. So yeah, this was initial design and it was working fairly well also. Why did we choose Postgres? Because it was easy to maintain and set up. It was available as a managed service offering, so you could do it, let's say, from AWS or any other cloud provider. Then we were familiar with the SQL model, and then it was there was no learning curve involved, so we just picked the tool that we knew. And then the initial focus was on building that MVP product and getting it live. So the focus was on building fast than building right. And then the product launching basically.
Yeah. So yeah, we built our MVP using Postgres, and the solution was working fine for a while. But we started noticing some signs that the solution might not scale. We saw some clouds looming over, and we saw the possibility of a storm. So we saw some signs that a storm was brewing. The first sign that we saw was slow updates. So even though the vehicle's data reached to our platform within few seconds, it was available to the user after some minutes in some cases. So even though we were getting it fast, it was being shown to the user after some delay. As a byproduct of this, we were getting complaints from the user that they are getting stale data, or if their vehicle was moving and it stopped, then they said, why isn't it showing that the vehicle is stopped? So we also saw increased latency on reads. So certain parameters such as what is the vehicle state? Is it stopped or moving? So this is dependent on the speed of the vehicle. If the speed is 0, then it's stopped. If not, it's moving. So even for processing some simple value which was dependent on the latest data of a vehicle, it took some time. There was a huge latency that we saw. And the third sign that we saw was occasional outages. So the way our platform worked was we had multiple applications, and all those applications were using a single RDS. Now this has both pros and cons. It's easier to manage, it's easier to maintain as well. But yeah, as a consequence of that, if just a single application is slow, it will affect other applications as well because they are using the same RDS. Then the first hunch that we had for the contribution to the storm is simply the number of vehicles. Now, if you see, this is the graph spanning from 2019 to 2021, where we had deployed our MVP solution. If you look at the y-axis on the left-hand side, you can see the number of vehicles increasing from around 200K to 400K. And if you see on the left-hand side on the y-axis, you can see the storage that we had on our RDS. It was increasing from around 1 TB to roughly around 4.5 TB in the span of 2 years. Now, it's simple to look at this and say that the rate of increase of the number of vehicles was way less than the rate of increase of storage that we were having in RDS. So this was a sign that maybe we are doing something wrong in the way we are storing the vehicle's data. So what do we do when we are faced with an issue? Well, the first thing that we thought of, we scale vertically. We saw increasing volume of data, so we first started increasing the disk for the RDS instance. Then we saw that even the IOPS were being affected because the writes were slow, the latency was high, and something was increasing the IOPS for the RDS. So we decided we should also increase the IOPS. We went from 20K to 40K, but you can't straight up increase IOPS for RDS. You also have to update the instance type, because IOPS is a function of the instance type. So we went from a 4x large instance to a 12x large instance, which is from a 12 core instance to directly a 48 core instance. So we just quadrupled the amount of cores to handle this use case. Now, obviously, we are scaling vertically. We will, of course, see performance benefits. But the underlying issue was still not resolved. So the next thing that we took a look at was performance insight. If you do not know, it's a feature that's offered by AWS for your RDS instances. It gives you information about your queries that are running on the instance. And it can give you information such as which query is slow, which query is taking a lot of resources. So we use this to identify queries which were expensive, and we decided to tune these queries, which is basically add indexes if they are not using indexes. And we also modified the queries to be more simpler and not make multiple calls to the DB or not hold logs for a long time. Now, obviously, we are improving some part of the system, but the underlying issue that we saw for serving the latest data for vehicle, it was still not resolved. The next thing that we saw was we analyzed the storage per table in our instance. So at that time, we were using a tool called as Table Plus. If you don't know, it lets you connect two databases and run queries on them. It has a simple feature called as item overview, which gives you overview of the tables that you have. Now, this is a demo table that we created, having the same schema and same updates done to it. And one interesting thing that we saw was if you take a look at the total size that we have for the table for around 1,000 rows, it was around 2 MB. But the actual data size was just 1 MB. So where is this additional 1 MB going to? To analyze this, we used the extension in Postgres, which is called as pz-stat-tuple. It gives you statistics on the tuples that are being stored for a particular table. If you don't know what tuple means, we'll cover that soon. So yeah, we analyzed the table. We found these interesting points. One thing we analyzed from the extension is if you see the dead tuple percent, it's around 83%. So we'll cover what that means in the next slides. So this led us to dig deeper and understand how Postgres works. So let's take a detour and understand what we found out at that time. The first thing that we found was what is MVCC. So MVCC is a solution that DBMS offer to solve a problem that is called as a non-repeatable read, which means that if a transaction is running, if it reads some data and another transaction comes and modifies it within that time, the first transaction which still not has committed, if it tries to read the same data again, it should get the same value. Now this is called a non-repeatable read, and MVCC is a solution to solve this problem. As the name suggests, it stands for multi-version. That means you have multiple versions of a row. And concurrency control, meaning if you have concurrent queries, you will give the correct version for a particular query at the time of read. Now this is a MVCC, and there are multiple ways to implement this. Postgres implementation or solution to this problem was to use a append-only storage model. So whenever you update a row, you copy all the contents of a row to a new tuple or a new row, and that will have a newer version. So you're basically having an immutable list of all the rows that were updated. And if you have multiple rows, you will have multiple versions. You might need a way to track which is the older version, which is the newer version. And it does so by maintaining a linked list. So yeah, and as you can imagine, now we are storing multiple versions for the same row. The storage would keep on increasing. The original design of Postgres was there to support all versions of a particular row. This was because at any point in time, you can go to a particular time and then decide what a transaction was reading at that time. But as you can imagine, this probably won't scale. You are having multiple versions of a row. To handle this, Postgres internally runs something called as vacuum, which will remove the versions that are no longer being used. So let's take a look at an example to understand this in depth. So suppose we are storing some vehicle information in this format where you have the vehicle ID, the event date time, and the speed for the vehicle. And internally, Postgres stores tables data in something called as a page. and page is usually fixed at 8 KB size in Postgres. Why 8 KB? Because disk read and write happen in blocks, and these blocks are usually of either 4 KB or 8 KB. So to make read and write efficient, it has set a page size of 8 KB. That means in one read operation, it can read a whole page. So, and within a page, you have the rows data stored, and within a page, it's called as a tuple. So suppose you have some vehicle's data with vehicle ID 101 with speed 55, and the vehicle slows down or downshifts, and the speed is now updated to 50. So if you run a simple query such as you're updating the speed and the event date time because you got a new message for the vehicle, you would see that Postgres internally would create a new tuple, a new version, and it will find the next available free space in a page. It will copy all the contents of the previous row, and it will just change the fields that were modified or updated. So how would you select data like this? Well, Postgres stores the data in tuples, and each tuple has some metadata. Within this metadata, there is a field which will keep track of the next version for a particular row. So if you were to run a simple query such as select star from vehicle where vehicle ID is 101, if you don't have an index, Postgres will do something called as a sequential scan. It will go through all of the pages. It will find the first instance of the matching row, and then it will traverse this linked list to get to the latest version of that particular row. So yeah, as you can imagine, now we have multiple rows for one single logical row. So how do we handle deletions of these versions? So Postgres runs a process that is called as vacuum after every interval and this is configurable. So in this diagram, the red rectangles represent dead tuples. Dead tuples are tuples which are no longer being used by any active transaction, and they have a version that is after them present in the table. And the green rectangles here represent live tuples. These are the latest versions of a particular row, or these are older versions which are currently being used by active transactions. So what vacuum does is it basically goes through each table, and since the last time it was run, it checks the tuples which are dead, and it removes the pointer to these tuples and basically makes them available for use for other tuples. Now, this doesn't actually give you space back on the disk. To get the space back on the disk, you need to run something called as a full vacuum. Full vacuum is a very resource intensive process, and hence Postgres doesn't run this automatically. You have to run this manually. And what it does is it creates a copy of each page, and it just copies the live tuples that are there from those pages. Now you shouldn't be running these on production systems because this will affect other queries performance because it's very resource intensive. So yeah, we took a look at two concepts, which was MVCC and vacuum. Let's take a look at another one, which is called as toast. So toast stands for the oversized attribute storage technique. As we discussed that Postgres stores data in pages, and pages are of 8 KB. Now what if you have some data that is more than 8 KB? Well, it splits such data into multiple chunks which are of 2 KB, and it stores this data separately in a different table and in separate pages. So how is the data toasted? So suppose we go back to the same example that we had. We have the vehicle ID, we have the event date time, and now we are storing the data within JSON format. So Postgres uses this toast mechanism for certain data types. These are either JSON, text, binary, basically variable length characters. And what it does is, if you have some data that is more than 8 KB, it will split it up into chunks. It will store it separately in a different table, which is called as a toast table. And in the main table, it will replace it with a pointer to the toast table. So whenever you are querying such data, Postgres will follow the pointer. It will retrieve all the chunks. It will assemble the message. And if it's compressed, it will also decompress it. And it will return the value. For our particular use case, we saw that every 30 seconds we are getting a message from a vehicle. So every 30 seconds we were getting a new tuple in the main table, because the event date time was updated. And every 30 seconds, the vehicle's data was also changing. So we were writing new toast pages every 30 seconds. So row updates would then modify literally all the chunks for a particular row. And we, as mentioned by Vinayak, we also had compression enabled. So this added some additional overhead. Every time you're reading, you would also have to uncompress this data. So MVCC coupled with toast was basically amplifying the effect of dead tuples. And essentially what we saw was around 50 or 60% of the data that we were actually storing was just dead tuples and no longer in use. Yeah, I'll hand over to Vinay.
Yeah, so till now we saw like multiple, I mean, as we were doing this, every month, you might have seen that the storage was increasing every month, right? So we were looking at the storage, we increased it like by 500 GB, and by the time we go into next month, it used to run out, and then we had to increase it again. And that's where we got into the details of Postgres, like how it is implemented and what exactly is going wrong with the tables. So then we started putting these pieces together, and there's this Swiss cheese hole models. This is basically used in aviation industry to analyze the air crashes and come up with the reasoning behind why something happened. So something similar that we have put, like, I mean, the issues that we were facing not happened just because of one of the things, but basically they aligned together. We had like MVCC combined with the toast implementation combined with the high volume of the data. That basically added up and then started creating the dead tuples or the bloat in our databases. So yeah, I mean, for our use case at least, this three coming together started creating problems. So yeah, so as this was happening, the consequences, the reliability of the platform was getting reduced. As the updates were slower, people were noticing that it's not getting updated as frequently as it should. Then yeah, the single point of failures, because let's say you're one of the application in that shared RDS instance. By the way, shared means it is still, there are logical databases that are separate, but physically it is just one database. But then that started affecting other applications because the storage is now running out. This will start affecting other applications as well. Then that basically became a single point of failure for us. And as we are increasing the instance type and the disk, the cost was increasing. And with RDS or any AWS resource, basically you can increase it but never scale it back, at least the disk part of it. So increasing or scaling the disk was expensive in this case. So we were paying close to like $20K per month. So all of this together, then we started looking for alternatives. Okay, how can we achieve the same use case but with a different tool? So we started looking for like another tool, a new champion basically. Then we consider, we jot down our evaluation criteria. What are we looking for? So the first criteria was that the reads and writes should be fast, because we were writing close to 10K records per second, and then half of that was getting read as well. So it should be as fast as it should be. Second was it should be horizontally scalable. It should not become a single point of failure. Let's say once one of the node goes down, it shouldn't stop the overall processing. So it should be a horizontally scalable solution. Then it should be a cloud agnostic solution. So today we might be on AWS, but let's say tomorrow we might go on a different cloud. So then it should be easy to move that kind of data store. So we are looking for something cloud agnostic. And then obviously the economical option, it should be, I mean, the operation cost for the tool should be lower than what we are paying for the RDS. So it should not be like astronomical cost that we should be paying. And last but not the least, it should be available as a managed service. So the updates and upgrades are managed by the team. We don't have to invest time and effort into managing the updates. And in case of disaster, the recovery would be swift. If it is a managed service, we don't have to invest resources to build that capability again. So then we started considering contenders. So the first contender was Cassandra. So we were using this Cassandra for storing the historical data. The parameters we talked about, right? Suppose if you want to look at that parameter for overall a month, then Cassandra was storing all of this data in it. So Cassandra was one option. So there is something called as a limit one query. So because data in Cassandra is stored in a descending fashion, so you can say give me the last record, so that record will be your latest record. So that limit one query can be used to get the parameter, but again the data model that we had in Cassandra was slightly different because we split the parameters and each individual parameter is stored separately. That's the data model that we had for Cassandra. So suppose if you have to serve the same use case from the Cassandra, then you have to read almost 2000 odd parameters from the Cassandra, join them back and then send it. That basically leads to a problem of read amplification. So you are just trying to read one row and that basically triggering 2000 reads from different systems. And that will also create a problem called tail latency, because you have to wait for the last parameter to be available, then only you can prepare a response and send it back. So this, although the data was available, but that was solution because of the read amplification and tail latency. So second one that we thought was the AWS memory DB. So again, it was a in-memory key value store. It is a implementation of Redis, but it has also backing of a disk. Because let's say your instances go down for some reason, then you could recover it from the disk that you have for the memory DB. It supports fast reads and write, but again, because of the disk, here also this solution is slightly costly compared to, let's say, if you get a plain vanilla Redis implementation. So the third option was going with something like Elasticache. So it was also a key value store that was storing everything in memory. So no disk was involved. We could deploy it in a cluster mode and create shards, scale up the shards as and when they are needed. And it was like very cheaper than the memory was basically cheaper than your database disk. And the ecosystem was also more mature, more people knew how to use it. There were tooling built around to including clients like Lattice, Redis. So you could choose between different implementation that you want to use for your client implementation. So there was a support available as well to connect with these kind of system. So we kind of went with then, okay, I think, yeah.
So we evaluated between multiple contenders and decided to go forward with Redis. Why Redis? Because as Vinayak mentioned, it was cheaper and it had a more mature ecosystem. So how did we migrate our use case from Postgres to Redis? Well, we were already having the vehicles data in Kafka. It sent the data to us, it was transformed and we got it in Kafka. So we just spun up a parallel consumer with a different consumer group, and this consumer was responsible to write the data to Redis instead of Postgres. The schema in Redis was similar. The key was the vehicle ID and the value was actual data that the vehicle sent, and the value also had the event date time for when it occurred. Now this worked for vehicles that were sending data actively. So, but we had some vehicles in the platform which were not sending us data for some time. This could be because of multiple reasons. Maybe the vehicle has broken down, or maybe the device which sends the data to us is not active. For such vehicles, the stakeholder also wanted us to cater to those. So we backfilled the data for such vehicles from Postgres to Redis. We essentially wrote a job which took data from Postgres and it moved it to Redis if there was not event date time which is lesser than what was stored in Redis. So we had now a parallel consumer, and we also had migrated the data from Postgres to Redis. To evaluate whether or not we have migrated the entire data, we took an approach which is called as random sampling. We took random subsamples of the vehicles from multiple customers, and we checked if we were getting the latest data for such vehicles. And once we were sure that we are getting the data, we switched the traffic from the Postgres application to now the application which was using Redis. And for a seamless switch, we used Kubernetes label selector. So the traffic was being served from Kubernetes service resources. We just pointed the service resource to point to the Redis deployment instead of the Postgres one. And yeah, the switch was seamless for the end users. Now, after verifying from end users and multiple customers that the latest data was being fed, we scaled down the older Postgres deployment. So why did Redis work well for our use case? Well, firstly, we wanted lightning fast real-time vehicle tracking, and Postgres wasn't offering this to us. Now with Redis, we were no longer going to the disk to get the latest data for a vehicle. We were instead just going to the memory, and Redis has a amortized cost of O of 1. That means on average, it will take around O of 1 time complexity to read the data for a vehicle. We were no longer seeing the bloat effects that we saw with Postgres implementation of MVCC along with Toast. And this led to an overall decrease in latency. We went from around 50 to 200 milliseconds using Postgres to just around 0.5 to 10 milliseconds using Redis. The second reason why it works so well is now we had essentially decoupled the architecture. We were no longer using the shared RDS instance. So even if we saw a burst of activity for serving the latest snapshot data, maybe we had more vehicles moving due to it being holidays or some other reason, it was now stored in a decoupled data store, which was Redis. It was no longer in the same RDS instance. This was also backed by Kafka. So if we wanted to scale the consumers horizontally, we can do that. And also the Redis itself was horizontally scalable. So if we were to see more vehicles come to the platform, we would require more memory. We can just add more nodes and more shards in Redis. The third reason was cost efficient. So we went from spending around 20K USD per month to just spending less than 3K USD per month in Redis. We went from a R5 12x large instance to 6 Elasticache instances of M6G X large. And the footprint of the data reduced from around 4.5 TB in the disk to just around 60 GB in memory. So nothing comes without any trade-offs. The first thing that we traded off was RDBMS capabilities. We can no longer perform complex aggregation queries. We can't join the latest data of a vehicle with some other table and do complex aggregations. We also lost out on asset transaction, asset guarantees that RDBMS systems provide. But we were fine by making this trade-off because the way we had partitioned our data, the key was the vehicle ID. So at a time, only a single consumer will update the data in Redis. So there won't be any concurrent writes, and we were fine by making this trade-off. The second thing we traded off was a manual recovery mechanism. Now, daily snapshots are available in both Elasticache as well as RDS, but RDS also offers something called as a point-in-time recovery. So if you have backed up your RDS and you run some query which was maybe it changed the data and you didn't want to change that data, you can recover to a particular point in time to just before you ran the query, and the data should be there in consistent format. But this was not available in Elasticache. With Elasticache, you are stuck with the last snapshot that you were taken. We were again fine by making this trade-off because the Redis was actually backed by Kafka. So if we were to, in some disaster, lose the data in Redis, we can just simply reset the offset in Kafka and it will replay the events on Redis, and we would have the latest data for vehicles. The third trade-off that we made was basically maintenance. It was an additional tool that the team had to learn to maintain, to manage, to use. But yeah, we were fine by making this trade-off because it offered great performance and great scalability. Now, after switching to Redis, we also made some further improvements. These were along the lines of compression. So again, the vehicles increased. We saw a huge bill for the Elasticache instances as well. And one of the contributing factor to this was the network costs for Redis. Every 30 seconds, we were sending the vehicles data to Redis, and AWS also charges for network transfers. So we could have chosen from a wide range of compression algorithms. These are some of the ones which we evaluated. The first is gzip. Gzip is very compute heavy, but it also offers a high compression ratio. We had Snappy, which is a little less compute heavy, but the compression ratio is a little bit lower than gzip. We had LZ4, which is very lightweight, but the compression ratio is way lower. And we had GSTD. It had like tunable levels of compression ratio versus speed. Among the contenders, we decided to go for LZ4 because it's very lightweight and the overhead of compression will be very less than the time it takes from reading from memory in Redis. So yeah, we implemented the LZ4 compression algorithm. To make the switch, we had to make sure that it was backwards compatible. We had to make sure that the readers were backwards compatible, meaning the readers should be able to read both the uncompressed and compressed version of the data. After making sure the readers were backwards compatible, we switched the writers to now write a compressed version of the data. And since we had ensured this backwards compatibility, in case we had to roll back, it's just as easy as switching the writers to again write compressed version, or uncompressed version. The impact that we saw of this was there was an overall 76% drop in the network in the network out, which is the reads. We saw a 74% drop in the network in or the writes, and the memory footprint reduced by 60%. We went from storing 60 GB in memory within 6 nodes to just 24 GB in memory.
Yeah. So overall, along this journey, the takeaways basically the takeaways that we came up with. Basically, picking the right tool for the job is basically the tool you might have used from the start, but then you need to know how that tool is working underneath. Because let's say one of the NFR changes, suddenly you have user growth on your platform, then you will start noticing that, okay, the tool is not performing as it's supposed to. So we need to pick the right tool for the job whenever, let's say, one of the NFR criteria is changing. So for that, you need to know the tools that you are working well. And in this case also, the Postgres really worked well for us. Like we started the platform around 2019, 2018. So from that time, it was working well till like 2021. And we then started noticing issues around when the scale grew. So that time we had to reevaluate the decision and go at the bottom of it. I mean, here also the first principle thinking comes into picture. Like if something is not working, you have to go at the bottom of it and understand from it, from the ground up. Yes, sometimes for the problem, you might just go on, throw the hardware. That hardware throwing will work for some time. But then if your scale is also increasing in the same fashion, then there is a limit that you cannot throw more hardware, because then throwing or scaling vertically is again expensive. You'll be paying more in terms of cost. So sometimes it is easier to go back and see if the model is right. Can we remodel it? Can we do something in the model? Or let's say we can use a different tool that suits our need that we have. As I mentioned, the architecture is not final. You have to reevaluate your tooling when, let's say, NFRs are changing. Yeah, migration, like once you close in on, let's say you are to move out of the tool that you are using, then you also need to convince the users and the stakeholders that are, let's say, relying on that system for using it. Because for them, the way they are going to access the data is going to shift. So it's like a mental shift, not just the data move. So you also need to get them on board that, okay, today you are going to access it using, let's say, queries, but then it is going to change. Now it is going to become a key value store. So that changes their interaction. So you also need to convince them or have the users also into the picture when deciding on these migrations. Yeah, the observability. So it's if the observability was not there, let's say the tools that we had, right, for us to detect that there are issues. If this observability was not there, then we wouldn't have detected those problems anyway. So it's, I mean, it's better to invest that time and money to get this observability there, so that you will be easily able to debug and understand where the issues are in your system. So if without observability, it's like flying blind or shooting in the dark. You'll never know what is improving. Even though you are making improvements, if you are not able to measure it using observability, then those improvements you'll not be able to like understand, is it really helping the system or not. I mean, with observability, you can do incremental updates to your system as well. Like you can change only one part and then see if it is helping or not. Yeah, and yeah, I mean, from the operation perspective, this needs to be there. The healthiness, is it slow? Yeah, and yeah, I mean, with observability, you can also predict when some failure is going to happen by setting up some alerting that you know that okay, some of the metrics that have happened in the past, then you can set up alerting using those metrics and get alerted or perform any preventive actions on that. Yeah, that's all we have for today. Happy to take questions.
And how many, so thanks. What is the sort of running cost currently in terms of dollars, and how many end customers are you supporting with this?
Okay, the question is what is the overall end-to-end cost of the solution and how many customers are using it. So as I mentioned, I mean, there are over 1 million vehicles out there in the platform. Basically, this is the system is not just built by us, but there are multiple other players are also involved. So getting an overall cost would be slightly harder.
Yeah, that's fine, but in terms of data, data is usually the biggest one. So.
Yeah, I mean, when we did this, right, we started using Redis like back in 2021. Almost 4 years are done, and then we are still using with the same configuration. We didn't have to make any change in that cluster. So from 400,000 to 1 million, it has scaled up now in terms of vehicle, and still we are able to serve with that with the same setup.
Okay, so around $20,000, is that similar ballpark?
Okay, for the Redis cluster,
yeah.
Redis cluster we are paying close to $3,000, including network and the nodes.
Okay, and how many end consumers who are actually tracking the vehicles or looking for the information?
Consumers are, I mean, vehicle to fleet owner. I mean, one fleet owner might have like multiple vehicles, right? So the users are less, close to 200 to 300k vehicles, customers.
So just on that note, I mean, when you started building the system, right, did you like inherit it like that, or did you build this right from the beginning while taking the decision of using Postgres?
Okay, I mean, the question is around decision of using the Postgres.
Yes.
Yeah, Postgres was, I mean, as I mentioned, right, it was like a tool that the team knew, and we were working on a particular tight deadline, right, or a go live date basically. And some of the features were already designed, and we were to just implement it. So that time the tooling, we decided that this is what we knew, and this is what the scale is. I mean, initially the scale was not very high, close to a 1 lakh vehicle or something, right? So with that scale in mind, we just built the initial MVP that time, and the solution just stuck around till the time we faced the issue.